Hey, everybody. So in this lecture, I'm going to talk a little bit about the beta distribution. So we're going to kind of go through some of the basic mathematics for how we use the standard beta distribution to solve practical problems involving the beta distribution. So that's the plan. And let me get the screen share going. Okay. So the general beta distribution is appropriate for situations where the random variable that we're interested in takes on a finite range of values. For example, the random variable might vary between 0 and 1, or say 1 and 10. Anyway, two numbers, two real numbers. And this fact that the distribution really takes on, or the random variable takes on only a range of values, one of those ranges not being infinity, makes this distribution unusual, at least relative to the distributions that we've talked about so far, where infinity is at least one of the limits, if not both of the limits. So this is the PDF for the beta distribution. And again, so this is going to be basically for the random variable taking on a specific value or realization, little x, bounded between two limits. In this case, we've indicated those limits are a and b. So those are the limits over which the random variable varies. And this function down here is called the beta function. And that is something that is going to be coded into any of your favorite mathematic programs. Like in my case, I might use Mathematica to find out the value of the beta function given values of these two parameters, Q and R. And it turns out Q and R are actually the two parameters for this distribution. So this is a two-parameter distribution. Assuming that you don't consider a and b to be parameters, they're just limits of the random variable, then you have to define Q and R in order to apply the beta distribution. So basically what you can see is you've got the beta function, one over the beta function pre-multiplying this quotient, which involves a shift of x relative to a, and then a shift in b relative to x, and then normalized by b minus a, and then the exponents here involve q and r, the two exponents, or the two distribution parameters. So just like the normal distribution, where we had a standard normal distribution, and that was special in the sense that the standard normal had a zero mean and a unit standard deviation. And we could solve problems using the standard normal by essentially transforming real problems, problems in which the distribution would not have a zero mean and a unit standard deviation. We could basically do a variable transform and transform that problem into one in which essentially the standard normal distribution applied. And then we could look up the probabilities in probability tables for the standard normal distribution. So it was a really useful way of evaluating probabilities. There's a similar trick we can play with the beta distribution. And that involves essentially what's called a standard beta distribution. So the idea behind the standard beta distribution is that we're going to define a special case of the beta distribution for which the random variable varies between 0 and 1 instead of varying between a and b. And as you can imagine, the reason that we're doing this is because we're going to show later on that you can do a variable transform and take any problem with limits a and b and transform them into the standard beta form, which is easy to solve. And so this is what the standard beta distribution looks like, or the PDF looks like. And basically you get this by just taking that previous beta distribution, or this PDF here. And if you set a to 0 and b to 1, voila, you get the standard beta distribution. And so it looks exactly like the beta distribution, except a and b have been set to 0 and 1. And our limits, of course, because it goes between, the random variable goes between a and b. In this case, it's going to go between 0 and 1. And one of the things that's kind of interesting to see is the various shapes that the standard beta distribution can take on depending on the value of its two parameters, Q and R. If we go back, by setting A to 0 and B to 1, we still have Q and R as our two parameters that we have to define in order to define this distribution. And you can see you get lots of different shapes to the PDF depending on the value of Q and R. So in this case, we've got a highly positively skewed PDF or form of the beta distribution. So when Q is 1 and R is 4, when they're equal to each other and equal to 3, you get something that looks more symmetrical. And then when Q is 4 and R is 2, it's looking negatively skewed. And then you've got this really cute example where when Q equals R and equals 1, it's actually uniform distribution. So the probability density is everywhere the same between 0 and 1. So that's called a uniform distribution. So lots of different shapes associated with these different choices of Q and R. So we can, of course, calculate a CDF from that beta standard beta PDF. And all we do is we just take that standard beta PDF and we integrate it from the lower limit, which is now a equal to 0, up to some value of x. And that's going to be our CDF, again, given Q and R. And the really interesting thing about this standard beta CDF is that if you look at this integral, it is exactly equal to the definition of what's called the incomplete beta function. And so that's going to be also in any of your favorite math programs, MATLAB or Mathematica. And the incomplete beta function, b sub x qr, so that's a little different than the beta function, which is just b of qr. So you've got that x in the subscript here. Basically just denotes that there is an upper limit, x, to the integral. And anyway, that incomplete beta function is exactly equal to this integral included in the standard beta CDF. Reason that's important is that we can basically replace the integral with an incomplete beta function. And so we have this really nice result for the CDF for the standard beta, which is just as the ratio of the incomplete beta function to the beta function. And the reason that's a really nice result is that it's very easy just to plug into your calculator or any math program the values of x, q, and r for the incomplete beta function and q and r for the beta function, take the ratio, and you get the corresponding CDF value. So this would be a really useful way to calculate probabilities, just like the standard normal distribution was really convenient for calculating probabilities for the normal distribution. But in order for us to take advantage of that, we have to somehow figure out how to do a variable transform so we can transform the general beta distribution into the standard beta distribution, which would allow us then to use this simple result. Okay, so that's what we're going to focus on next. We're going to start with that general beta distribution, which again looks like this. So we're just looking at the PDF of the beta distribution. We've seen that before. You can see that the limit goes from a to b instead of 0 to 1, so you know it's the general form. And the corresponding CDF is just going to be the integral of this PDF from the lower limit, which is now a, up to some specific value of the random variable x, which is bounded between a and b. Okay, so that should all look very, very similar. I'm just going to take this definition of the beta distribution CDF, move it to the top of the next page. That's where we are here. And now I'm going to perform a nifty little variable transformation on the integral. So I'm going to let a new variable y equal the dummy integration variable s minus the lower limit divided by the upper limit minus the lower limit. And you might ask, where does this come from? Well, you can see that by transforming s into this form, basically y is going to vary between 0 and 1, which is, of course, what the standard beta distribution independent variable does. How does that work? Well, think about the limits of s. So s goes from a at the lower limit, and the maximum value x can take on here is b, so s goes between a and b. So when s is equal to a, this quantity y is going to be 0, so that's the lower limit. And the upper limit occurs when s is equal to b. And so when s is equal to b, you can see that this ratio here is just unity. And so that's the upper limit 1. So basically, we're transforming s, which can go from a to b, into y, which goes from 0 to 1. And the reason, again, is that that's going to, if we can successfully pull this off, then basically it's going to transform our general beta distribution into a standard beta distribution, which is our goal, because we can easily solve that one. All right, so let's take this variable transformation and just kind of run with it. You can see that we've got a couple of different components to this integral that we have to replace. We have to replace ds with something involving y, or dy. And we also have to replace this quantity here, b minus s. We have to replace this quantity s minus a. We don't have to worry about b minus a because it's really just a constant relative to the integral. And then we have to deal with the change in the limits too. So these are all things we have to consider. Let's go one step at a time. So let's start with trying to figure out what ds is going to look like under this variable transform. We just take the derivative of both sides. The derivative of minus a is just 0 because a is a constant. And so we end up with the dy is equal to ds divided by b minus a. That allows us to solve for ds, which is just going to be b minus a times dy. So that's the replacement for ds. For s minus a, that's fairly straightforward. We can just take the definition of y here and solve for s minus a, and we get that s minus a is equal to y times b minus a. For b minus s, it's a little more tricky. We just have to do a little bit of algebra, but what we find is that b minus s equals 1 minus y times b minus a. So there are some of the key components of the integral transformed into our y variables. So we just substitute. And so we're substituting a y times b minus a for s minus a. And so we're going to end up with y to the q minus 1 times b minus a to the q minus 1. That's where that comes from. Just substituting y times b minus a for s minus a in this integral here. Likewise, we can substitute b minus s into the integral, and then we're going to substitute this quantity on the right-hand side, so that becomes 1 minus y raised to the r minus 1 times b minus a to the r minus 1. We also substitute our new definition for ds, which is b minus a times d minus, or times dy. And when we do that, we actually end up with an extra b minus a here, which we can take into the denominator. And in fact, we can separate this quantity here in the denominator into b minus a to the q minus 1 times b minus a raised to the r, but then we end up with an extra b minus a to the minus 1, and so that's incorporated here as that minus 1. And so, of course, the really nice thing about this form is we can see that we're going to see a lot of canceling across of terms across the numerator and denominator. So I want to go ahead and take this integral and move it to the next page, and I'll show you that. So this is the same integral we just saw. Now we're going to go ahead and simplify, so cross out some of the terms that we can get rid of, and we're left with this much simplified integrand. And of course, the other thing that we've done is we've applied the limits. I should go back and just make sure that that's clear. So if we look at the original integral, when s was equal to a, let's look at our definition of y. When s was equal to a, y was equal to 0. So the new variable y, or integration variable, is going to be 0 at the lower limit. Likewise, when s was equal to x, in our new transform for the variable y, that upper limit is going to become x minus a divided by b minus a. So that's where the limits come from here in the variable transformation. And so that's where we're carrying those limits through here. Now, the key thing to note, and Siri is hearing me again, the key thing to note is that if you look at the integrand here, that is exactly our standard beta distribution, right? It's got the same form, y to the q minus 1 times 1 minus y to the r minus 1 divided by that beta distribution, or that beta function of q and r. And so that means we have successfully transformed our general beta distribution using this variable transform for y into the standard beta distribution and it looks exactly like the CDF for the standard beta distribution, except that our limits are a bit different. Instead of 0 to x, we now have 0 to this x minus a over b minus a. Okay, so I just moved our CDF to the top of the page here. And then we finally finish up by saying, hey, look, if this is just the standard beta distribution, we can use our previous result that the standard beta distribution is just the incomplete beta function divided by the beta function. And in this case, instead of x subscript here, we've got u, which is our upper limit, and that's going to be x minus a divided by b minus a. So the bottom line is that we can solve the general beta distribution problem using this very simple result for the CDF of the standard beta distribution just by performing this variable transformation here, setting u equal to x minus a over b minus a. And likewise, if we were interested in the random variable, the probability that the random variable was, say, going between two bounds, x1 and x2, we would just take the CDF for the upper bound, that is x2, and subtract from that the CDF for the lower bound, x1. And that's what I've done here. And this is basically from the class notes showing exactly the same thing. Here's our probability for, given by the beta distribution that the random variable is going to be between x1 and x2, or is going to take on values between x1 and x2. And again, that's just going to be the difference between the CDF evaluated at x2 minus the CDF evaluated at x1. The other thing that we can learn if we take the expected value and the variance of this distribution is that the mean of the distribution can be expressed this way, and the variance can be expressed with this equation. And so we're going to use these expressions in our next problem to estimate values of Q and R given the mean and the coefficient of variation. Okay, so speaking of example, let's get right to it. So this is example 3.32 in the book. The duration required to complete an activity in a construction project has been estimated by the subcontractor to be minimum duration is 5 days. It's going to take them at least 5 days to complete the project. The maximum duration is 10 days, and the expected duration is 7 days. The coefficient of variation of the required duration is estimated to be 10%. So given that information, we're asked to calculate the probability that the activity will be completed within 9 days, assuming the duration of the project follows the beta distribution. All right, so let's think about this a little bit. We've been given the mean, because that's, of course, the expected value of the beta distribution, which is going to be here equal to 7 days. And we've also been given the coefficient of variation, which, of course, is the variance divided by the mean. So we can solve for the variance and then use that. We're going to have two equations and two unknowns, Q and R, and we should be able to estimate values of Q and R from those two equations. So let's go ahead and do it. We start with the mean value. So they say the expected duration of the project is 7 days. So that means they're talking about the mean is 7 days. And of course, from our previous result, we saw that the mean was equal to this expression here. We also know that the minimum duration of the project is 5 days. The maximum duration of the project is 10 days. So we can kind of plug and chug here, put in 5 for A, 10 for B, and we end up with, after solving for Q, that Q is equal to 2/3 R. So we have this nice relationship between Q and R. Now we just need one more equation and we can find the value for both Q and R. And that additional equation comes from the coefficient of variation, COV, and we're told that that COV is 10%. Let's just go back to the problem statement. It says the COV of the required duration is estimated to be 10%. So we know that the COV is 10%, and remember the COV is defined as the standard deviation divided by the mean. And so we just substitute the mean in the denominator, and then all the rest of this is just the square root of the variance, which we were given an expression for here. So we just take the square root of both sides of this set of that equation and plug it in, and that's what we get here. Furthermore, we can substitute for Q 2/3 R And when we go through that exercise, we get this equation here, which is only in terms of r. And we can solve for r, kind of going to the next page. And when we solve for r, we get this expression, evaluate it algebraically, and it works out to 6.75. And then if we plug that 6.75 in for r, we get for q that it's 4.5. So let's come back to the problem statement then, because it took us a while to get the two parameter values for this distribution, Q and R. We were asked to calculate the probability that the activity will be completed within 9 days. Okay, so that really means that we're looking for the probability that the random variable for time to completion is going to be less than or equal to 9. And that we can evaluate using our standard beta distribution by first evaluating what the corresponding u value would be, which is just going to be the time t equal to 9 minus a over b minus a, which works out to 4/5, which is equal to 0.8. So the incomplete beta function is going to be evaluated for u equal to 0.8, q equal to 4.5, and r equal to 6.75. And then accordingly, the beta distribution is going to be evaluated at those same two values of q and r. And here I've written a little script for Mathematica in which I've defined this function, CDF beta, in which x, q, and r are variables that we're going to pass values to. That's why the underscore is there. That colon equal just means we're defining a function. And then we're calling the beta function, which is incomplete in this case because we have this x and then the q and r value, and then divide that just by the beta function, which is beta qr. So these beta functions are essentially functions that are embedded in Mathematica. So that's the definition of the CDF beta function. And then if I evaluate that CDF beta function for a u of 0.8, or x in this case, 0.8, q 4.5, and r of 6.75, I get 99.8%. And so that's the answer. Oops, that's the answer. Basically, the probability that the job will be completed in less than or equal to 9 days is 99.8%, according to the beta distribution. And the last thing I wanted to finish up with was just a table from chapter 6, actually, which goes through kind of a laundry list of the different analytical probability distributions that you might want to know. And it's kind of cool to look at this list because we've now covered in detail virtually all of these distributions and even then some. So we know about the binomial distribution and the geometric distribution, the Poisson distribution and the exponential distribution and the gamma distribution and the shifted gamma distribution and the normal distribution or Gaussian distribution, the log normal distribution. We haven't really talked about the Rayleigh distribution, but it's not too complicated. It's actually pretty similar to the normal distribution. There's the uniform distribution, which actually, remember, the beta distribution conforms to in certain limits for Q and R. But basically, that just says there's equal probability density between the two limits here, A and B. There's a triangular distribution, which we really haven't talked about. Then we have the beta distribution and a couple of additional distributions, the Gumbel and Weibull distributions, which we really haven't talked about. But and then of course there's the hypergeometric distribution. There's the negative binomial distribution. So there's other distributions that we actually have talked about that are not even on this list. So the bottom line is I think you should feel really kind of happy, proud, confused perhaps, that we've really covered quite a few of the analytical distributions which are used for a lot of practical problems. And so with that, I will say goodnight and thank you for watching. See you later.